Okay, so today I will start the organic spectroscopy portion, and I think that this organic spectroscopy portion is very much important topic, and in the organic spectroscopic portion that mainly consists of the NMR, that IR, UV visible spectroscopy, and the Raman mass, and the atomic absorption and atomic emission spectroscopy. So in this portion, we know that the spectroscopy means that the interaction between the particulate with the electromagnetic radiation. And from that portion, from that spectroscopic method, we will get or we will know that from the electronic transition, from the functional group analysis, we will know that which molecule is present in that particular sample in which amount. So that means the spectroscopy gives that particular idea. So the spectroscopic application is huge in the organic chemistry portion. And now today I will start the basic concepts of the organic spectroscopy series is the NMR. So this NMR is basically the huge portion, and I will like to start this portion with the concept of the 10+2 level. Okay, so we will know from that particular chapter atomic structure that what is atom, what is nucleus. Okay, and with that particular thing, with that particular chemistry, and we'll amalgamate with that physics of the 10+2 level, and we will apply the some concept of the magnetic field. So first of all, we will think about that what is NMR. That the NMR is basically that the NMR means, what is NMR actually? That NMR means that is the nuclear, M stands for the magnetic, R stands for the resonance, and other one is very much important, that is the spectroscopy. So in this portion, we'll have to know that what is the nuclear magnetic resonance spectroscopy. Now first, let's consider one thing, that this is an atom. Now this is an atom, and with that particular atom, this is an atom, and in that particular atom, there is a presence of one thing, that there is a presence of one nuclei. Okay, so this is the nuclei. And with that, the outside of that particular nucleus, there is a presence of the 2 electrons, and this particular 2 electrons are there. Okay. So like basically the sun and planet phenomena. So there is a 2 electrons are there, and these 2 electrons are revolving around the nuclei, or they can spin on its particular position. So either they are revolving, okay, around the nucleus, or they can spin on its particular position. Now what is happening? This nuclei is made up of the 2 moiety, that is proton and the neutron. And we all know that proton is the positively charged and neutron is the neutral one, and this electron is the negatively charged. So later on we will discuss that how this proton and electron, that particular these two can give the positive charge and negative charge due to the upward and downward theory is responsible here. Now there is an electron is rotating, okay, on its particular position or spinning on itself. Means this is one electron, okay. So this electron either rotating on this side, or this electron is rotating either this side. So what is actually happening when this electron is rotating on this particular direction or on this particular direction? So there is a obviously formation of an important thing, that is the angular momentum due to the spinning of electron. So due to the spinning of electron, there is a production of the angular momentum. So this particular angular momentum, they have the particular formula like this, that is the root over I into I plus 1 into h by 2 pi. So you can think, sorry, this is the S. For the electron, we will consider this is S. So this S into S plus 1 into H by 2. So for this S, here S is the spin quantum number. Here S is the spin quantum number for the electron. Okay. And so if there is a spin quantum number, so there's obviously a magnetic quantum number is there. A magnetic quantum number is there. Okay. Magnetic quantum number, and this magnetic quantum number we will denote it like the ms. Okay. So up to this, that electron is spinning on its particular position. They can produce the angular momentum due to the spinning, and that's why they can produce the spin quantum number, and later on they can produce that particular electron produces magnetic quantum number. Fine. So if this particular electron is rotating or spinning on its particular position, why not this nuclei is rotating? Okay. Yes. In 1924, okay, the eminent scientist Pauli stated that if the electron is spinning on its particular position, then this nuclei can also spin on its particular position. Okay, so that this statement is very much important, that this is the nucleus. Okay. And this nucleus is rotating either on this side or on this side. Okay. So this is the nucleus. Now, so this rotation of the nucleus is obviously, this rotation is due to some charge. So here the charge is a negative charge, and we all know that in the nucleus there is a proton and neutron is present, and proton is a positively charged. And due to this positive charge, this new rotation of that particular nucleus is occurred. Okay. Now, so if the electron is rotating, the nucleus is also rotating on its particular position. Now, obviously, there is production of the angular momentum. There is a production of angular momentum, and that angular momentum has the formula I into I plus 1. That h by 2 pi. Okay. So that what happens in this case, that particular I is the spin quantum number. That particular I is the spin quantum number. So obviously, due to the spinning of the nuclei, the angular momentum is produced, or we can say that due to the spinning of the nuclei, there is a production of an important thing, that is the magnetic moment. That is the magnetic moment, that is mu. And we will discuss later that what is the actual effect of the magnetic moment on that particular NMR. Now this spin quantum number is produced, that is the I. Okay. So obviously there is the production of the magnetic quantum number. There is the production of the magnetic quantum number, that is the Mi. Here, so what happens actually, this up to this we will get an idea about the spinning of the nuclei, and due to the spinning there is a formation of the spin quantum number, and as well as the spin quantum number is formed, so there is always a production of the magnetic quantum number, and this particular magnetic quantum number, it has a very much important effect on that particular NMR. So that we will complete, I will complete the nuclear portion, and this nuclear portion is very much important, that how the nucleus is spinning, okay, and what does it affects. Now I will move forward to the magnetic portion. Okay, so up to this the angular momentum, up to this this is the nucleus is also spinning, and they will produce the angular momentum like this. Now in the 10+2 level, that is the one particular subject, that is in the physics, the chapter is there, that is the magnetic field, magnetism. So in that magnetism, there is a one topic is there, that is a magnetic effect of the electric current. Okay, that is the magnetic effect, okay, of electric current. So this is the magnetic effect of electric current is there. So what happens when the any charge is moving, okay, so there is obviously a production of a magnetic field. Okay, so here also, if the electron is rotating like this, if the electron is rotating like this direction or like this direction, okay, or like this direction, so there should be a formation of the magnetic field. So if the electron is rotating, okay, so there is a magnetic field is produced. So why not for the nucleus? Obviously, for that particular nucleus, okay, so there is also a production of the magnetic field will occur. Now what is happening? If the electron is rotating, okay, if you will think about the electric current, the current flow from the positive end to the negative end, and the electron is flow from the reversal of the direction of the current. Now what is happening from in here? Actually, we will apply the left hand rule of the Fleming, and then we will get the two pole of the magnets. Now for that particular electron, we will get here, that is the south pole, and here like north pole, and here the south pole, and here the north pole. Okay, and for that particular nucleus, that is reversal is happening for that particular nucleus, that we will getting the north pole here, we will getting the south pole here, and we will getting the south pole here, and we will getting the north pole here. Clear? Now, so if this direction, then this thumb is in the upward direction. So this upward direction can denotes that there is the north pole is there. Okay. Now there is a very much an important topic that is not as much related as like the for the NMR, that for the S block. We are all aware that there is some S block elements are there, and S block will know that in the S block they are accommodated the 2 electrons. Okay, they are accommodated the 2 electrons, and this particular 2 electrons are very much paired in the high intensity or higher strain. So actually what happens in this case, that if you will see that there is a production of the south pole, and there is a production of the south pole like here. Okay, so actually what happens now, if this south pole and this north pole of another electron is there, so there is a huge attraction with each other is happening. Okay, and there is also the attractive forces increasing, so that they can pair up, and their the force is required to break this electron is very high. So that's why I put this electron on this adjacent position, okay, to know that how much how they strongly attached with the covalent bond. Now this south pole and the north pole, and south pole can interact, and they can form this diamagnetic form. Okay. Now move towards the basic portion and move towards the concept of the NMR. Now we will get that this nucleus. So our main focus for this chapter is on this portion, on the nucleus, because electron has no such of effect on this particular NMR. Now this nucleus is acting as a Cheney magnet. Okay, so basically what is happening, okay, for this particular nucleus, when we will keep in an NMR instrument, and how they give that absorption spectrum. Now basically what happens in this case, that now let assume that, okay, or you can get an idea. Let assume that that there is a basically what happens in this case, that you have a nucleus. Okay, so this nucleus is like this. Okay, so this is the nucleus. Okay, this is the nucleus, and this particular nucleus is rotating like this, and they can form a Cheney magnet on the, they can produce a dipole moment or the magnetic moment. Now when the nucleus is in the free state, okay, they can move anywhere, means they can rotate to every possible direction, I mean to say that this is the nucleus is there, okay, and this particular nucleus having the north pole and south pole, what actually happens in this case, that they can rotate like this, or rotate like this particular direction also. So they can move towards any possible direction. Okay, when there are no such an external magnetic field will apply. Okay, so this particular state is known as the degeneracy. Okay, that is a very much important point, that the degeneracy. So what does happens, that if the nucleus is there and nucleus is itself act as a magnet, so this particular magnet can rotate in every possible direction. Okay, so this particular state is known as the degenerated state. So to stop this such a phenomena, okay, to rotate the everywhere or in every possible direction, so we have to put an external magnetic field. So if there is a north pole is there, okay, and there is a south pole is there, clear? So we will put an external magnetic field and name this magnetic field like B naught or H naught. Okay. So this B naught or H naught. Now what happens when we will put the external magnetic field, okay, and I will think about that is a B naught equal to 1.41 Tesla. So at first the nucleus is in the degenerated state. When we will put the external magnetic field of that particular magnetic strength 1.41 Tesla, then what happens? This nucleus will try to align with that particular magnetic field. So that this is the north pole, this is the south pole, okay, and the nucleus, okay, and the nucleus is trying to align on this position. So we will say that this nucleus is aligned, okay, aligned with the B naught or H naught. It means that there is a north pole and there is a south pole, there is an interaction is there, huge interaction, and there is a north pole and south pole interaction will there. So actually what happens, there is a potential energy will going down. So due to the decreasing of the potential energy, when it align with the external magnetic field B naught, it will become more stable. Okay. So first degenerated state, then this nucleus is kept with an external magnetic field. Then what happens? This nucleus is trying to align with that particular external magnetic field. So that is the main concept. Okay. So I'll think about that. This is the B naught. Okay. This is the B naught. So first it is the degenerated state, the nuclei. Now when the B naught is there, this nucleus is on this particular direction. Okay. Now what happens? After the basically and what is happening in the NMR instrument actually? Now that there is basically a radio wave generator is there, means there is a radio frequency source is there. Okay. So this radio frequency is suppose He. Okay. Now when there is an application of the external magnetic field with that particular nuclei, what is actually happening? There is the formation of one thing that is very much important, that is the precessional motion. That is the precessional motion. Okay. So precessional motion of what? Precessional motion of that particular nucleus. Okay. And that particular nucleus can not increase the precessional motion in that huge amount. Okay. So with which frequency with that precessional motion occurs, means that external magnetic field, okay, this is the nucleus, okay, and there is the one external, there is a north pole and south pole is there, and what happens, this nucleus is in the degenerated state, they try to align with that particular magnetic field. Now there is a production of one frequency of that particular nucleus. That particular frequency is known as the Larmor frequency. That particular frequency is known as the Larmor frequency. Okay, or we can say this is the precisional frequency on which frequency that particular nucleus can rotate. Okay, can spin on its particular direction. Now, so we will see that if the B naught is 1.41 Tesla, means the external magnetic field strain. So the omega or the for Larmor frequency or precisional frequency, that omega equal to 60 megahertz. Okay. So the omega is 60 megahertz means with that particular 60 megahertz, this nucleus is aligned with the magnetic field. Clear? Now this. So basically, the precisional frequency of that particular nucleus is 60 megahertz. Okay, that is the standard for that particular nucleus. And our radio frequency is, the source is, I think I put that is a 90 megahertz. Okay, that is a 90 megahertz. So actually, what is happening now? This is the h nu, and they can rotate with the frequency that is omega. Now what happens? This when that particular precisional frequency of that particular nucleus is matched with the radio frequency value, then this nucleus come against the magnetic field. Means what happens? What I try to say that this is the north pole. Okay, this is the south pole of the external magnetic field, and this nucleus is aligned with the south pole and north pole, and its precisional frequency is 60 megahertz. When this precisional frequency is matched with the radio frequency, then it comes like this. Okay, and they can align against the magnetic field. So actually what happens, this nucleus is there, okay, means external magnetic field is first there, then it has a possible two direction like this or like this, means with the align with the field or align against the field. Clear? Now this portion is very much important for understanding some important relation between the energy and like this type of some important symbols are there. So when it will be absorbed, means I will say that when h nu equal to h omega, then only this nucleus absorb the energy, absorb the radio frequency, then it will come against the field, means then it will come on this particular position. So actually what happens, this is the nucleus and this can rotate like this and they can come against the field. Okay, they can align against the field. Okay. So after the absorption of the frequency, which is the same with the precisional frequency. Okay. So this particular frequency is known as the operating frequency. Okay. So move forward for on this particular topic. Now what is actually happening, that there is basically the free nucleus is there, okay, free nucleus is there, and with that particular free nucleus, that is the degenerated state, okay, that is the degenerated state. So when the nucleus in the degenerated state, I will put the one external magnetic field. So this external magnetic field is B naught. Okay. Now, so if we put the external magnetic field, and so before I will write down one thing, that let us assume one nucleus. Okay, one nucleus. Okay, that is you can assume that 1H1 nucleus for the hydrogen atom. So this particular hydrogen atom, what is happening? That I will write down the I equal to half, means the spin quantum number is half. Okay. So if the I equal to half, so what is the number of possible orientation of nuclear spin. So that is equal to 2I plus 1. Okay, and that particular thing is also known as the magnetic quantum number. Okay, that is the magnetic quantum number also. Now, so number of possible orientation of the nuclear spin is 2I plus 1. So this 2 into half plus 1 means that 2. Okay, so they have the spin quantum number is half. So they have the possible two direction like plus half, okay, or the minus half. Okay, so this is the two possible direction on which the nucleus can rotate. So the first, so if you will put the applied magnetic field, external applied magnetic field, so then what happens? They can split into the two portion, either plus half or the minus half. So plus half state means that they can go like this and like this. So this is a very much important point, that this is the plus half and this is the minus half. This is the plus half, this is the plus half, and this is the minus half. Okay. So actually what happens, and this state will be known as alpha state, and this state is known as the beta state. Means the free nucleus is there, that is the external magnetic field is B naught, okay, and the nucleus is rotating with the magnetic field, okay, or against the magnetic field, okay. So that plus half means that is the plus half and that is the minus half, means that is the plus half means that is the lower energy state. I will describe in the previous point that why the energy will decreasing due to the north pole, south pole and south pole north pole attraction. That due to that particular reason the potential energy goes down, and there is the production of the alpha state, and this alpha state denotes there is a lowering in energy. Now this plus half and the minus half, there should be a huge energy gap, and that particular energy gap is the del E. So this del E is very much important, and they have a significant effect on the beta naught, and this del E and beta naught are quite directly proportional with each other. So actually what happens when we will increasing the magnetic strain means first of all beta naught is 1.41 Tesla, okay, and that omega is equal to 60 megahertz, okay. So and we will get the daily value is 2.39 into 10 to the power minus 5 kilojoule per mole. Okay, that is the, and that also the temperature is the 25 degrees centigrade, or the 273 plus 25 equal to 298 Kelvin. Okay, so if we will put this type of condition, then we will get the daily value is 2.39 into 10 to the power minus 5. So if we will increasing the beta naught from 1.41 to something 2.36 Tesla or 2.41 Tesla, what happens? This omega value is increasing like the 100 megahertz. And what is the omega value? The omega is the precisional frequency of the nucleus, on which frequency the nucleus is trying to precise, okay, trying to rotate on its particular position. Means first with the field and then against the field after the absorption of the radio frequency. Now we can assume that del E is directly proportional with that particular beta naught. Okay, so this del E we can say that this is a function of B naught. Okay, so this del E is the function of the beta naught, then put an important thing, that function of gamma into beta naught. Okay, so this ratio is very much important. Okay, and this gamma is known as the magnetogyric ratio. So this magnetogyric ratio means, or that is the diamagnetic ratio, means that is completely dependent on the energy difference and the external magnetic field, and the ratio between the basically the magnetic moment, okay, and the basically the dipole moment. Now So up to this we will get an idea about the how the spinning will occur when we will put an external magnetic field, okay, and there is a production of the two state, one is alpha and another one is beta. Alpha is the lower energy state, means we can write the align, okay, with the field, align with the field, and this is against the field, against the field. So against the field means that is the V naught, and here is also the V naught. Now actually what has happened that that all the nuclears, okay, in that that they are not giving the NMR spectra. So which type of nuclei they can give the NMR spectra? So this is the very much important topic for the discussion. So now now I write basically the three states, okay, which are being very much important for the, which are given the NMR spectra. Now this is the first is the even, okay, means there is a proton and there is a neutron and there is a spin quantum number is 1, okay. So even odd, okay, odd even and odd. So there is I can write the 1, 2, 3 and 4 cases are there. So actually what happens for the even, this 0 is come for the spin quantum number, and these are the NMR inactive. These are the NMR inactive. Like the, you can say that the 1608, okay, 12C6, okay, means the proton number is 8 and the neutron number is also 8. So proton number is 6 and neutron number is 6. So actually what happens in this case that they are neutralizing with each other and becomes this spin quantum number is 0. Okay. Now even odd and even, there is something are there that that is the basically the half, 3/2, 5/2, means they always come into the fractional form. So that is they are the NMR active. They are NMR active. Okay, like the 19F9, they are NMR active. Okay, several nucleus are there on this particular two condition. Now order, that is very much important. For the order, there is a 1, 2, 3, the whole numbers are there. Okay, and they are also NMR active. They are also NMR active. For that particular reason, the very much important point of discussion is there. That is for the order. That is the 1H1. Okay, so there is a several use that 1H NMR. Okay, so 1H NMR means what? That 1H NMR means number of proton equal to 1, neutron number is 0. So order, and this is the NMR active. Okay, and what happens? Now there is a isotope of this hydrogen is the deuterium, the D21, and this hydrogen is NMR active, but the proton number is 1 and neutron number is 1, but this deuterium is not actually NMR active. Okay, so this is the actual point, and the description of the which of the nucleus is NMR active and not NMR active, NMR inactive. And there is another point is very much important. There is a 13C6. Okay, that proton number is 6 and neutron number is 7. Okay, so basically on this particular thing that is not comes here, that is basically comes here. There is a 13C NMR. Okay, that 13C NMR is actually NMR active, but 12C NMR, 12C is not actually NMR active due to the same number of proton and the same number of neutron. Now, so there is basically this is the atomic mass is there, atomic number are there. So they are all different. Okay, so to quantize this type of nuclei, okay, that will have the formula like this. Basically, the del E equal to function of B naught. So daily equal to function of gamma into B naught. Okay. So that if we will quantize that particular atoms, that particular nuclei, which having the different atomic mass in a NMR instrument. So this daily equal to function of gamma B naught into h by 2 pi equal to h nu. Okay, because they e to equal to h nu into c by lambda. So what is happening? This h is cancelled out, and we will remove the function portion, and gamma B naught by 2 pi equal to nu. So therefore the nu equal to that is the very much important relation, gamma B naught by 2 pi. So this portion, when will all quantize, so this equation, that is the huge important equation, that nu means the frequency, and the relation between the frequency and the magnetic field, we will see that is the directly proportional. Okay, so the actually the first equation we will get that nu equal to gamma into B naught by 2 pi. So this is the very much important equation. Okay. So now move to the another topic, that we will understand the three main things, that is a nuclear, there is a magnetic, there is a resonance, means resonating with the radio frequency, and the frequency, precisional frequency of the Larmor frequency of that particular nucleus, which is put into the NMR instrument. Okay. For getting the absorption spectra. Now what happens actually, that is the B naught. Okay, so that is the B naught is there, and this is the, that is the external magnetic field, and this nucleus is there, and this nucleus is splitting onto this particular two division, that is the plus half, and this plus half is the basically the alpha state, and beta state, that is the minus half, means against the magnetic field, and that is the, this is the magnetic field direction. So this is the against the magnetic field, and this is the with the magnetic field. Okay. So there is a term is there, that is a very much important term, that is a population density. That is a population density, and that population density plays a very much crucial role. Okay. In NMR for getting a continuous peak. Okay, so if as I draw a structure of the one nucleus, okay, that is not happening in the actual in the real NMR instrument, because if you will put the ethanol sample, there is a crore numbers of ethanols are there. There is not possible for one ethanol molecule or one hydrogen nucleus is analyzed for the NMR instrument. So now what happens actually, that is a population density plays a crucial role, and for that particular reason the very eminent scientist, that is the Maxwell, put an equation that n upper by n lower, okay, n upper means that is the beta state, n lower means that is the alpha state, is equal to e to the power minus daily by kb into t. So that particular equation, okay, so that particular equation is very much important, that nu by nl is equal to e to the power minus daily by kbt. Okay, so that is the Maxwell equations. Okay, and why this equation is very much important for getting the absorption, continuous absorption spectra. Now, if you will think about that the three conditions are there, and these three conditions are very much important, okay, for better understanding that how this Nu and Nl, okay, are the responsible for continuous NMR spectra. That Nu by Nl is equal to 1, Nu by Nl is less than equal to 1, and Nu by NL, that is greater than equal to 1. So according to this law, okay, so what happens if we will see that this is the north pole, the external magnetic field, this is the south pole, and this there is a assume that there is a 1, 2, 3, 4 and 5 nucleuses there. Okay, and this 1, this 2, this 3, this 4 and this 5. So actually what happens, 1, 2, 3, 4, 5, and so there is a equal population density. That state is known as equal population density. So when this equal population density will come, okay, that means we will assume that comes into the point that Nu by Nl equal to 1, means that there is a in the alpha state and this is the beta state. So the number of nuclei in the alpha state is equal to the number of nuclei in the beta state. So actually what happens, this is the saturation is come, and when this saturation is come, the no absorption spectra is actually gives to the NMR. Now, when if you will think about this, there is a north pole and this is external magnetic field. So this 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, and okay. So at first, if you will think about that there is the basically the 10 nuclei are there. 1, 2, 3, 4, 5, 6, 7, 8, and 9 and 10. Okay, so these all 10 nuclei are present in the with the field. Means alpha is complete consisting of the 10 nuclei. Okay, so when they are consisting upon the 10 nuclei, so after some time being, when the h nu is equal to h omega, this all 10 nuclei come again to the against the field, means beta state. Okay, so this is that is not actually gives the high resolution peak. So for getting the high resolution peak or better peak, what you will do, that there is the basically if you will put the 1, 2, 3, 4, 5, 6, 7 or 8 nuclei. Okay, or the 6 or 4 ratio. 1, 2, 3, 4, 5, 6 and 1, 2, 3 and 4. So this 6 nuclei is in the with the field and 4 nuclei is against the field or on that particular external magnetic field. So actually what happens in this case, that is the basic portion, and so when there is a when the h nu equal to h omega, this one nuclei is goes against the field, and then there is a relaxation process is occurring. I will discuss the relaxation process on later. That then when it will come and like this on this against the field, and again it will comes with the field. Okay, so to maintain the population density, this particular nuclei have to relax. Okay, this particular nucleus have to radiate some thermal energy. Okay, so for getting the continuous peak, this phenomena is very much important, that Nu by Nl is less than 1, means the Nl should be greater than Nu, or you can write that N alpha should be greater than the N beta. Okay, so that is the number of molecules or number of nuclei that is present in the alpha state should be greater than the number of molecules present in the beta state. So actually what happens now, how we will increase the alpha number of molecules in the alpha state. So that's why this Maxwell equation is very much important. And if we will think about this, okay, so for increasing the number of molecules in alpha, okay, we will have to increasing the daily. Okay, so to increasing the daily, our aim is to increasing the daily for reaching the N alpha is greater than the N beta condition. Okay, for getting the continuous peak. Okay, so actually what happens, this to increasing the daily, we'll have to increase the external magnetic field. So when we will increase the external magnetic field, then what happens, this when we will increase the beta naught, B naught, okay, then the that omega is increasing. Omega means that is the precisional frequency of that particular nuclei is increasing. When this precisional frequency is increasing, there should be the increasing of the del E, and this particular, when the del E is increasing, there is a effect on the Nu by NL. Or when we can decrease the beta naught, or we can decrease the beta naught, okay. So but decreasing the beta naught is not our aim. To increasing the beta naught, okay, that the omega value is increasing and del E is increasing, so Nu by NL is comes into less than 1. So we will achieve that particular Nu by NL is less than 1. This is a very much important condition to getting the continuous absorption spectra. So actually what happens, that up to this we will get some idea about the population density of that NMRs to get the continuous peak on that particular NMR spectra. So to achieve the Nu by NL is less than 1, what to do? That increasing the B naught. To increasing the B naught, omega is increasing, and if the omega is increasing, that the difference between the two states means there is a del E, and del E is also increasing. So if the del E is increasing, means the number of molecules is present 1, 2, 3, 4, 5, 6. Okay, so number of molecules in the alpha state is increasing. So Nu by NL is less than 1. So up to this I will discuss about the nuclear portion, magnetic portion, Maxwell law, and what is the application of the Maxwell law in the population density. Okay, so basically for the 2 million molecules, okay, for the 2 million molecules, okay, what is actually happening, that in the ground state or in the alpha state, the 9 molecules are in excess. 9 molecules are in excess, okay, in alpha state, and this excess is known as the population excess. This excess is known as the population excess. So this is the basic or fundamental concept of the NMR, and now on the later on the next video I will try to discuss about the relaxation process, and there is a spin lattice reduction, spin relaxation, and shift towards the absorption spectra and the chemical shift portion. Thank you.